In our previous session, we learned about magnetic field and magnetic field lines. In this session, we will learn about magnetic field due to a current carrying conductor. Students, here I want you to recall first activity 13.1, which we have learned. From this activity, we understood that an electric current through a metallic conductor produces a magnetic field around it, right? An electric current carrying wire, it was copper wire, it has produced magnetic field around it. In order to find the direction of the field produced, let us repeat the activity in some other way. So this activity only we are repeating, but in other way. For what are we doing this activity again? This activity we are going to do for knowing the direction of the field. Okay, by activity 13.1, we observe that it produces magnetic field. But what will be the direction of that field? That we will understand now. For understanding this activity, we will need a compass. We'll have a long, straight, thick copper wire, 2 or 3 cells of 1.5 volt each, and a plug key. And we need to have arrangement as shown in first figure. Look at figure number 1, first figure. So we have to make arrangements as shown in the figure. Place the straight wire parallel to and over a compass needle. So in circuit we have a plug key and 2-3 cells. Now how do we have to place the straight wire? It is parallel and it is over a compass needle. Observe the direction of deflection of north pole of the needle. So we will get in which direction the north pole is. If the current flows from north to south, as shown in first figure, the north pole of the compass needle would move towards east. In this figure, we are also shown 4 directions: north, east, west and south. Now we know about north and south pole of compass needle, that it behaves like a bar magnet, and we know that how the magnetic field is from now north to south pole. Now you see, in between north and south we have which direction? East, right? So what happens if the current is flowing from north to south direction? In which direction the needle will move? In east direction. Why is it so, students? Again I am saying the field lines will be from north to south pole, right? And in between north and south we have which direction? East. So if the compass needle moves towards east direction, that means that the current is flowing from north to south direction. Then we have to replace connection of the circuit as shown in the second figure. Then what will be the difference? This would result in the change of direction of current through the copper wire, and that is from south to north. You will be thinking, why is it so? I tell you, in the first figure we have placed a battery, a cell, in such a way that the positive end of the battery of the cell, that is on left hand side, you see in the first figure. And we know that the current moves from positive end to negative end. So the direction of current will start from left hand side in the first figure. Students, see the arrows how it is made, right? Now look at the second figure. What is the difference in the arrangement? Now the positive end of the cell, that is on right hand side. Look at the figure. So what will be the direction of current flowing? Current will start flowing from positive end to negative end. So in the second figure, it will be starting from right side. Is it clear, students? Okay, so in the first figure, we were having the deflection of the needle from north to east direction. What will be it in the second figure? In which direction the needle will move? So in this case, the needle will move in the west direction. Why is it so? Look at the small figure which shows the directions north, east, west, south. Here, the direction of electric current is in which it is from south to north direction. Right, students? Okay. Now, if it is from south to north direction, in between we have west directions also. And to reach from south to north, that has to be west direction. So that is the reason that the needle of compass will be deflected towards the west direction. And this means that the direction of magnetic field produced by the electric current, that is also reversed. So by this activity, we can learn that we understand the direction of magnetic field. Now let us learn magnetic field due to a current through a straight conductor. What determines the pattern of the magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? Let us understand an activity for this. Here we are going to learn about magnetic field produced by a straight conductor. For this, we will need a long, straight, thick copper wire. We will need a battery of 12 volt. Then we will need a variable resistance, that is rheostat. We have learned in chapter number 12 what is rheostat. We know that it is a variable resistance. And for what it is used? It is a component used to regulate the current without changing the source of voltage. So we don't need to change the battery, and we can regulate the current. Then we need to have an ammeter. What is an ammeter? Which measures the electric current. We will need ammeter of the range 0 to 5 ampere. Then we'll need a plug key. Also, we will need connecting wires. And then we have to connect all these electric components as shown in the figure. How do we have to do it? We have to insert the thick copper wire through the center. And how? Normal to the plane of rectangular cardboard. We will need a rectangular cardboard, and you see how it is placed. That rectangular cardboard and the long copper wire should be perpendicular to each other. Look at the figure carefully. Okay, so perpendicular to each other we have to fix, and we have to fix it in such a way that it does not move away. Then we have to connect the copper wire vertically between the points X and Y. So wherever we have attached this copper wire, that will be points X and Y. And then in series connection, a battery, ammeter and a plug key. What do we need? We will need here some iron fillings. We will take these iron fillings and sprinkle uniformly on the cardboard. We need to keep the variable of the rheostat at fixed position, and we need to note the current through ammeter. Then close the key so that a current flows through the wire. We need to ensure that the copper wire which is placed between points X and Y remains straight. So copper wire must remain straight throughout the activity. Then gently we will tap the cardboard for few times and will observe the pattern of iron fillings. Previously we have learned an activity, and we have learned through that activity that iron fillings align themselves in a pattern. Okay, so here also what will we observe? We will observe that iron fillings align themselves, showing a pattern of concentric circle around copper wire. Here in figure B we can see what will be the pattern. It will be concentric circles pattern. Concentric circles means what? Which will have single center and all the circles around it same center, right? And this way the patterns will be circles. I am sure that you know what are concentric circles, right? The circles which have same center. So this way the pattern of the iron fillings will be. Can you see what do these concentric circles represent? I'm sure by now you all know that they represent magnetic field lines. We have learned through this activity. If you want to find the direction of magnetic field, how will you find? Previously also we have seen that in the activities we used a compass needle. So here also we can place a compass needle at point P over a circle. Okay, on any circle select a point, name it as P, and there you place a compass needle and observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines. As we know that the magnetic field lines emerge from north pole and complete it emerges at south pole. So here also the direction of the north pole of the compass needle will give the direction of the field lines produced by the electric current through the straight wire at point P. And in the figure you can clearly see that the direction of magnetic field is shown with an arrow, which means it is starting from north pole. So that will be the direction. Now, what happens to the deflection of the compass needle placed at the given point if the current of the copper wire is changed? If we'll change the current, what will happen to the compass needle? We will see that the deflection in the needle also changes. So remember students, if the current changes, the deflection in the needle changes. If the current is increased, the deflection also increased. What is the meaning that the deflection increases? The needle move fast. So if the current changes, deflection changes. Current increased, then the deflection also increase. It suggests us that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases, because when the compass needle moves, when it deflects, when it gets magnetic field, right? So if the current is increased, the magnetic field also increases. And when the magnetic field increases, it show increased deflection in needle of the compass. So remember, if the current increases, magnetic field increases, and if magnetic field increases, the deflection of needle will increases. Another question: what happens to the deflection of the needle if compass is moved away from the copper wire and the current through the wire remains the same? So here, if we keep compass away from the copper wire, we know that when compass is brought nearer to the copper wire, then it produces magnetic field. If we move this compass away from the copper wire and we keep same current through the circuit, then what will happen? For that, we can make changes in the point of the compass. Somewhere else we keep, and we can say that point Q. Then we need to change observation. We will see that the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. And from figure, we can note that the concentric circles representing the magnetic field around a current carrying straight wire become larger and larger as we move away from it. So the question was, if we change the position of the compass needle, then what will happen? If we keep it away at some distance, then what will happen? So if the distance increases, which distance? Distance between compass and copper wire. If the distance between these two increases, then the magnetic field decreases. Please keep this in mind. If the distance increases between compass and current carrying wire, then the magnetic field decreases, and as a result we will have bigger circles of magnetic fields. Okay, so from this we have learned that if the current increases in the circuit, then the magnetic field increases, and as a result the deflection of the compass needle increases. If the distance between compass and copper wire increases, which means move if we move away the compass needle, then the magnetic field decreases because the distance has increased. So magnetic field decreases, and as a result we will get larger and larger circles for magnetic field lines. So this is all about magnetic field lines due to a current through a straight conductor.